All right, it says it's recording. It's good. All right. So welcome everyone. My name is Roger Silva. And today we're going to be having our second paper discussion from the PSI subspace section. This one is about data visualization in the neurosciences, overcoming the curse of dimensionality. This is a paper from Elena Allen and others that came out in Neuron 2012. This was just around the time 2011 to 2013, where there was kind of a heated debate and discussion about how meaningful visualizations of brain images and functional connectivity and other modalities were for brain imaging in general, and whether they were conveying useful information. This is just a snippet of that debate, and kind of like just as one perspective of what came out in different publications at the time. But I'll get more into that later. Just to give you guys some context. This meeting or gathering is usually it's designed to be a kind of like an engaging kind of approach to a journal club. It's more of a seminar format where each person who wants, each volunteer takes on a role, and these are some of the roles that we had available for this talk, like the scientific peer reviewer, the archaeologist, the academic researcher, private investigator, social impact assessor, and the hacker. And each one of those has a very specific role that has been described here. This is based on Colin Farrell's seminar. I've shared information about this before. The idea is that each one of these roles will look at the paper from a different perspective. Who are the authors? What kind of impact has this paper had in the field? Do they provide code? Can we replicate the results? If we were to the person or the reviewer looking at the paper, what kind of a review would we write about it? And if we were to find this paper out of the blue, what context did it come in, and what was happening at the time, and why was this paper important? And lastly, in this particular role, the academic researcher, what would be an interesting project to consider as a follow-up to this one? So it's less about reviewing the contents of the paper. It will happen organically, but it's also more about the impact and the significance and the relationship to other things. It's more like contextualized understanding of the paper. So generally, I have people about a week ahead of time come in, volunteer for these roles. They will read the paper and maybe put together 1 or 2 slides with comments, depending on their role. So for today, I think it was maybe a bad choice of a day, or problem with a bad choice of a week to have this. I didn't get any other volunteers to participate, so I'll be taking on most of these roles today, all of them actually. I'll try my best, and the hope is that you guys will interact with me. I'll try to make stops. If there's anything you guys don't understand, feel free to stop me anytime. So with that, let's get started. So I kind of used the NeurIPS format because it had better guidelines. The Neuron journal, I couldn't find a good guideline for reviewers. It was kind of generic, and this is kind of like an opinion piece. So I didn't feel like their guidelines for review were the best for this paper. So I just used the one that I had used last time from NeurIPS. And it's basically going over summaries and contributions and strengths, weaknesses, and so on. So this is from the perspective of a reviewer. This is and yeah, this is the peer reviewer role. So in summary, this is a paper that surveys the use of graphs in neuroscience papers in 2010. It was published in 2011 or 2012, submitted in 2011, I think. And it evaluates ways in which irresponsible use of graphs can be misleading. It highlights the importance of displaying uncertainty in graphs. It demonstrates that, at least in 2010, many published graphs were lacking a description of uncertainty. And I think probably the most important part is that it puts forward guidelines for identifying fallacies in various graph choices, as well as evaluating and improving the display of relevant information together with uncertainty. And that's a key point. It's an emphasis on uncertainty display in graphs, particularly in the case of high-dimensional data. And so they propose some interesting solutions, especially for brain imaging data that I think were not available at the time. And to this day, I don't see those being used very often. So I'll discuss that perspective a little later. And finally, it proposes to follow the principle of show more, hide less, which is the idea that you want to show as much of the data as you can, balancing not to be overwhelming and getting to the point. But the idea is fundamentally you don't want to hide the data. You only hide as much as you have to, and you try to do it in kind of an organic way as much as possible. And there are examples of that I'm going to go over. So next, here's my perspective as a reviewer in terms of strengths. Maybe before I go over these strengths and weaknesses, I will walk you through the paper. So the paper is relatively short. I think it's like 3 to 4 pages long. And it basically gives some motivation at the introduction and brings in this point with a reference to Howard Weiner, actually I believe is a statistician from the 90s, who made these important remarks about uncertainty, that visualizations must remind us that the data being displayed contains some uncertainty, and sometimes we don't get that information, obviously from graphs. And when I say graphs, I mean like plots of any kind, scatter plots, bar plots, and so on, and also figures. And also that visualizations characterize the size of that uncertainty as it pertains to the inferences we have in mind. So if we're trying to compare groups, make sure that those measures of uncertainty, say if you're displaying variance, that they represent maybe confidence interval instead, depending on the kinds of tests you're trying to, or inferences you're trying to make. So like I said, this is an opinion paper, and this is probably the most awesome, one of the most awesome parts of the paper, the set of guidelines that they propose. Can you guys see it well? Can you read the text here? Yeah, so the way this is organized is like a question answer kind of thing. So there are main categories here uh, about the design and organization of your graphs, uh, the axis. This is talking about referring to indicating the scale of the graph, whether they are labeled, if the limits are appropriate. And here on the right side, it provides some solutions, right? Some examples of different situations, how you would go about labeling. So if you have units, you should specify them if they're well defined. If the units are not well defined, well, you could indicate that it's arbitrary units. And if the thing you're displaying is not, simply does not have a unit by definition, like correlation, then you don't need to include it. So uh, these are just basic recommendations, but useful in the evaluation of uh, you know figures and graphs as reviewers and as authors ourselves. Some interesting points about color, the use of color in color maps. What types of color maps are recommended depending on the type of data. This is a limited description, but gives a general idea that you can expand later. Uh, so these type of color bars recommended for bipolar data that can take positive and negative values, and mapping 0 to green is in this case. So right at the middle of the uh, color bar is important. Having your color bar be symmetric, I would say, is a really important one that many times is missed out. If the data is unipolar, meaning it only has positive or negative values, then you would use something like this. A color map that has only one, it indicates only one direction from dark to bright. It could be hues of blue, for example. And if the data is circular, like many times when we work with Fourier transforms and frequency domains, uh, use a color bar that is circular in nature, meaning that the end maps to the beginning, the end maps to the beginning again. Even though this is uh, unwrapped as having a beginning and an end, any point here in the middle could be the beginning and end because it's circular by definition. The last color is the same as the first. Uh, and here, the points that are most important, really, I think, for this paper is the display of uncertainty. And I want to take time to read these questions here. So a recommendation is to check, does the display indicate the uncertainty of estimated parameters? And is the type, this is like a yes, no question. You should make sure that the answer is yes. If you're the author and if you're the reviewer, you would want to recommend ways in which that could be achieved by the authors. And is the type of error surface appropriate for the data? This is a tricky one, especially if you're talking about brain imaging, how do you represent uncertainty in that case? So in general, are the standard deviations or prediction intervals useful to describe variability in the population? You want, if that's the case, then you want that information in there. If the standard errors or confidence intervals are useful to make inference about parameters estimated from a sample, that's another situation. You also would want to have these standard errors presented. And another situation to consider, if parametric confidence intervals they should only be used if the data meet the assumptions of the underlying model. And this is making a point that many times with small samples and I mean, even with larger samples these days, The distributions are not necessarily Gaussian, which is the underlying assumption of many tests. So non-parametric tests would be preferred in that case. And there are going to be examples down below that I'm going to show where the data is, for example, bimodal, and how they go about how you go about presenting the distribution informs you about whether a particular confidence interval is really meaningful. And here, the last point are the units of uncertainty defined. And this is to say, well, if you're using error bands in your plots, then what is the meaning of that band? What is it representing? Is it a 90%, 95% confidence interval, or something else? Is it with respect to the median or with respect to the mean? And so on. There are other recommendations here for annotation and coloring that I'm not going to get to, but this is a very thorough, well thought through set of guidelines for evaluating graphs that I personally find very useful and highly recommended. So moving on, the next part of the paper looks at a survey. Basically, they took 6 journals in neuroscience, all of these: Frontiers in Systems Neuroscience, Human Brain Mapping, Journal of Neuroscience, Nature Neuroscience, Neuroimage, and Neuron, and sampled 288 articles that were published in 2010 from these journals, and examined all figures in those 288 articles, which total 1,400 figures. And for each one of them, they were looking at 4 specific points. First one is if there was a dependent variable or a quantity of interest, and if that was labeled. The second was to check if the scale was indicated for the dependent variable, and when applicable, if the measure of uncertainty was also displayed. And lastly, if the type of uncertainty, say standard error or error bars, was defined in the figure, or at least in the accompanying legend. And here is an example of 2 depictions. This is considered like a 2-dimensional data. This is 3-dimensional data. This is 2-dimensional because you have only X and Y axis, whereas here this is 3-dimensional because you have X, Y, and the color is the 3rd dimension. And in this case, it's the color, or the grayscale, is depicting the dependent variable. So they were looking at these 4 bits of information over these 1,400 plots. And this is a little summary of the results. Basically, for what they observed is that for 2-dimensional data, most plots had all of these 4 features, with uncertainty being significantly less present in those plots. And interestingly, when moving on to 3-dimensional data, these types of images here, then the quality and in terms of availability of this information went down considerably. Even for things like naming the dependent variable, meaning the color bars did not have an indication of what it was representing, if it was a t-value or if it was a z-score or so on. And the scale, it typically comes out, so that's it's still, there were situations, and I think there's at least at the time there was software that displayed color bars without scale indication. So there was a significant decrease here in proportion. And yeah, I forgot to mention, this is proportion 0 to 1. So 1 is 100% contains the information, and like 40% means only 40% had the information. In this case, the variable, the label variable. So the more striking point was that for images, the information, meaning three-dimensional data, the information regarding uncertainty was just absent, or in most cases it was absent. So that is a concern, and was a concern at the time, and a point that they were trying to address in this paper, proposing solutions. So that was the survey, and I'm going to move on to the next part. The principle of show more and hide less. And here is an interesting example of less information going to more information. It's the same data. There are three categories, and they are interested in comparing the means. And so basically, I think there are three different treatments, and this is the response that you measure for each one. And some of the interesting things here is start with a bar plot indicating the error bars, that indicating that it represents the standard error of the mean. And this is fine. But the second part here, it's showing the same data now using box plots. And some interesting things show up here. First, that whereas the bar plot was limited or lower bounded by 0, we observed that some of the data actually had negative values. So this plot is giving that information to us, which was not available in the previous one, that the data can take on negative values. And the other thing is it's giving us information about skewness, for example, for this second measure, that it's heavily bright skewed. It still gives the same information in terms of can you distinguish the mean? You can clearly see that the means are undistinguishable for these three tests. But we can start to get some idea that the distribution of how the distributions are quite different between these three treatment levels. And finally, again, the same data plotted now with violin plots, where you use a kernel density estimator of the histograms to build this density estimate of the data. And you overlay it with the same box plot from before. So you get all of the nice information that you had here, but now you also get a sense of the distribution. And with this one, we see that the third population actually has, it's bimodal. So if you were doing a test of the means here, you have a very obvious violation of the Gaussian assumption. If you were using like an ANOVA test, one-way ANOVA. So something to keep in mind, that in this case, if you were to make comparisons based on the mean, maybe the mean is not the most interesting feature to be looking at to begin with. And I think this is the final example. This is probably the most interesting one. It's looking at EEG data, a case for EEG data, and a case for fMRI data. And here, this is an ERP from estimated from after an ICA decomposition. And it's showing the average ERP for, I think it's subject-specific ERP, so it's for a given subject. And it's looking at the average of trials where the subject made an error. And the blue one is the average of trials where the subject made correct, gave a correct answer to the test. And this is fine and gives the information, shows all the time course. We can see the difference in the response very clearly. But this one on the right has a lot more information. Specifically, it shows these band plots where you can see the variability at each time point of the measurement. And we can see that the variability is much higher on the error condition. And that's mostly because the percentage of trials where the subjects make a mistake is much smaller. So you have fewer samples, fewer instances of error trials to average. So when you create this ERP, they naturally have a higher error band. The other thing that we see here is a depiction of what the error bar or the error bands represent. Here they represent a 95% confidence interval. This is non-parametric testing because clearly the data is not Gaussian. It's a time series after all. Then we also see an indication of what was the reference time point used to align the time courses before averaging, and an indication of when the stimulus that led to potential errors, basically the test stimulus when it was applied, when it was given to the subjects. It also shows, very interesting here, the time points where the difference between the correct error response and the error response were statistically different. And this is implicitly already corrected for multiple comparisons because it's comparing time point by time point, and it's a non-parametric test. And it also gives you an idea of what is the test that you're conducting with this p-value, what is the meaning of this significance. And so it's giving that the null hypothesis is that the mean activation at a given time is the same for the error and the correct trial. And then the alternative is that they're different. So this is the definition of the test. So you get all of this nice information very well summarized, and it enriches this original graph so much more. And this can be achieved by going over those questions at the beginning in the guideline. The last example here is the one that I'm really excited about. This one is a traditional GLM model of auditory oddball, I think, novel minus standard contrast. And you're looking at the change in the beta weights of the regression. And what it's showing here is an overlay of the fMRI response on the areas that are significantly changed or statistically significant at some arbitrary threshold, possibly corrected for multiple comparisons. And you're seeing it overlaid on the anatomical image. This has been a point of contention around that time since 2011, that what they call the data to ink ratio was extremely small in fMRI. And the data here is the color part, the fMRI information is what you're trying to show. But the amount of ink you spend is much higher, much bigger. The idea is that you spend a lot more ink printing the anatomical underlay than the amount of ink you spend to present the data. So this was a point of contention, and people were saying, well, it's possibly meaningless, or it's not useful. You're just wasting ink, kind of, or you're just wasting space. You could just give a textual description, and it would be as informative as looking at the image. At least that was the argument at the time. And here is an improved version of that same display that to this day I don't see often in papers, and I'd be happy to be corrected if I'm wrong. But what this is showing is sort of an extended version to begin with of the color bar. So now the color bar has hue going left to right, which is basically the color change, just the same as before, same ranges. But now it also has a transparency level. And the transparency level is where the uncertainty is introduced in this plot. So the value that is controlling the transparency is the t value. And the t value has built into it like the standard error. So it's kind of giving you an account of the uncertainty in the data. And naturally, what it does is it makes areas that are not statistically significant, that don't have a high t value, high statistic, they become transparent, meaning they're not important, or we don't have as much certainty about it. So that's what happens here. We still have the same underlays, but because of the alpha level, where areas where that measure of uncertainty is not so small, they're not so small. Yeah, I think yeah, small. Then you get no, uncertainty is high. Yeah, where uncertainty is higher, you get smaller t values, and it becomes transparent. So you don't see the data there, but you do see more data than before, way more data, and you actually get to see, for example, the areas of the default mode network that were not visible before. And it's interesting, a few years later, I think 2008, I can't remember who was it, but there was this rediscovery of the default network and as a thing, and and it, it it was largely because up until that point, all the spatial maps that people looked at were thresholded. So they never saw that there were areas of the brain that were activating an what's the word, anti-correlated with the tasks, which is typical of default mode. I should say they were anti-correlated with extrinsic stimulants. So interesting that this kind of information pops up naturally if you hide less of the data. And that was the point. And you still get all the same value. If you use the same arbitrary threshold as before, you can just display it as a little contour that's indicated here. This black contour outlines exactly the same area. But you're able to see much more of the data and take much more, how do you say, much more valuable information from the displays. The graphs here in the bottom are, let me remember, these are, I think, averages over the significant area of the beta values for each subject. There were 28 subjects, and this gives yeah, there were 28 subjects here, so 28 samples basically for each of these tests that you're conducting voxel-wise. And this is just to get a sense that the information is consistently showing an increase. In this case, this is what the beta value for the standards was. This is what the beta value for the novels was. And you see that the change going novel minus standard is positive because all values are here. It's consistent with that information. And it's just displaying it in a sort of summarized way. So that's a wrap up for an overview of this of the ideas presented in this paper. And to wrap up my role as a reviewer, I'll just say, yeah, I'll just say that I think I'm getting some feedback. Is anyone trying to say something?
Yeah, I hear them too, but I didn't hear it. I don't know where it's come
Okay.
from.
I think it was just an open mic. I already closed it. So in terms of strengths, I think it was a well-conducted survey with quite a lot of work, I'd say, if I had to do it myself. And these were just the two main authors, I think, who did this part of the work. The guidelines that they provided I think are very valuable. Actually, the paper comes with demos for all of the figures that they showed. In the sense, MATLAB is kind of limited. In these days, it's better, but at the time, it was limited in what it could do for controlling transparency and having these two-dimensional color bars. So they put together code on how to, and you can see example data and code of how they went about doing that. It's MATLAB specific and it's 10 years old now, but still relevant, I think. This is something that I had not mentioned, but I like very much is one is this little thing in the corner. It's so useful, and I actually don't know how they did it. I'd like to go and figure out. But so they're showing proportion versus proportion, right? And on this range, the data is all concentrated in this 0.7 to 1 range. So it's better to present the data within this range. But this little thing here gives some comfort in the sense that they're able to show the 0, 0 corner. I just like the aesthetics of it. And the other cool thing here is this outline. This is a kind of a multivariate confidence interval, or in this case, bivariate, I should say. So it's showing the confidence interval as ellipsoids. And I think you get that from multivariate tests. And that's something that I don't see often enough, and I find very useful for, in this case, they're comparing journals. But for comparing, different groups, it's very interesting to have these overlays or underlays in with your scatter plots. And my last point is just that there's code for all of these and regenerating all these figures. And so it's I highly recommend looking at this if you have a chance. And in general, I think it's insightful that the information is correct and it's presented very clearly. In terms of weaknesses, the only one I could think of is that maybe it lacks a little bit of contextualization, and the discussions that were going on in other papers at the time might have been because they had already published a response to some criticism in a previous year. Might have been because of that. And because of that, I gave it a score of 9 out of 10 as a reviewer. I'm familiar with the field, so I'm confident about that score. I don't think that they discuss the broader impact, but it's implied in the way that they present the different guidelines and the limitations in the survey that they did, especially. They're not explicitly talking about changing the field, but I think it's important and implied from the survey that it hasn't. It was bound to have an impact. No discussion of bias and harm. I don't think it's a concern there. And overall, I gave it an accept as a reviewer. Up until this point, is there any questions? Are there any questions? Remember, you get the most if you interact with me.
So I have two comments, not like a question, but I can wait until end, whatever you prefer.
We can do it now.
Okay. So I agree with you. It's a very good paper. I like the two part that I really like was the fact that show more, hide less, and also the figure that you were spending time on it. I think that was a very important point that we usually choose arbitrary threshold and we miss all those important information. I even do it most of the time. So I think these two are important part that I really like about this paper. And I usually like go back and read this paper, just make sure I'm following the comment. The two things that I feel can be improved in following work is the fact that there are less talk about they talk about the importance of the color, especially for the grayscale, and also like in the printing grayscale, and also in table one. But there are like a different category of the color that can be used to enhance visibility. The other point that I feel needs more exploration is the importance of the visualization in the very high dimensional data, which I think was not the big problem at that time, I think. I'm not sure. So the paper didn't talk much about, okay, if we have like a super high dimension, how are we going to visualize it? So that's another point that I would like to make. Which I will share a paper that is not about visualization. It's about like a tip to for dimension reduction that I think can be useful when you want to visualize the high dimension data. Those are my comments.
I didn't get your last point though about data reduction.
So when we have a high dimension, we need a way to visualize it, right? And usually, like we have like different, like we have circuits and many other approach, but they are usually like they include so much information is that we may miss the important part. So it's important what dimension you want to present and how you want to present it. I don't know if I couldn't find any information in this paper that can help to better visualize high dimensional data. That's what I'm trying to say.
Okay, yeah. I mean, what I can say is it's true. They're not addressing particulars of data that goes beyond images. But what they presented with the solution here, let me show you for illustration. With this um, with this example here about the thresholding, what they're showing is that you can represent many more dimensions by overlaying. Is one way by overlaying information and playing with this transparency. So transparency you can think is now another dimension. Right? So you have three types of information here. You have the underlay, which is the anatomical location. Obviously, you have X, Y, Z coordinates, so that's another three dimensions. So we're at four already. And we also have the color for the activation and the transparency. So this is like 5 to 6 dimensional description. Uh, just just on this very small representation and very complete. Beyond that, yes, it gets hard. We are limited creatures by definition. So there are other ways of looking at data, and it becomes more interactive. You have to kind of slice the data differently to get a sense. I've seen plots before there is this course I was taking, and let's see, they had some examples here, I think. And there were some examples in here of very high dimensional data. I think it was hyperparameter tuning that they were discussing. And I can't remember the name of the plot, but there was a very interesting plot that they had. Linear models. No, this is hyperparameter tuning. Sorry. I'm just looking for the example of the plot that they had for looking at very high dimensional data. Might be this one. Takes a second to load. Not this one. Maybe this one. If I can find it here, right now, I will let you know later what I was referring to. Yes, not here. So never mind.
Yeah,
I'll get back
catch for me
to that later. There is another one. It's like plotting vertical lines, and if you make it interactive, then you can section the data to restrict your view to a particular range of values, and that when you see how that reflects on your other variables. So if it's interactive that way, it gets easier to find patterns. But I can't give an example right now. I have not seen other great solutions, and I don't know everything. So yeah, if you ever become aware, let me know of what is a good solution for that. There's T-SNE plots, but they're highly nonlinear and hard to interpret. And I don't know if that's exactly what you would want every time. And there's also the issue with yes.
You said TSNE plots, like stochastic neighbor embedding.
Yeah.
Okay, because I've been working with that and with principal component analysis, and I was wondering like what would be like an appropriate selection of parameters of each of these tools, and like try to make them as robust as possible when including or excluding data points, because I see that they are quite not robust.
So I'm not exactly sure what you mean by excluding data points. In general, it's not recommended unless you have good reason. Like there was an error during data collection. But is that what you're referring to? Like dropping a data point? Or
yeah, not specifically that, but like I was playing around to see the features, the feature space when changing, like by removing or including one data point to see how robust it was, like the TSNE to the number of data points, and also I changed the parameters, and I saw that the feature space was very, very different. So it is very difficult for me to interpret like the resulting graph.
Yeah. So typically you need to have some external information like about the data. In our applications, we have things like the age of the patients, and each point is a patient, or we have some labels, like for MNIST, they have digits, right? They know the digits, and for our data set, you could have patients in controls, or there are other categories. It could be different trials. So if you have that extra information, whatever you're trying to compress, at the end you can label it differently based on those labels, and you can start getting a sense of how it's partitioning the data. if you don't have that, it's non-interpretable really by definition, because it's just a highly nonlinear transformation embedding really in a two-dimensional space, and it's going to be a different transformation every time you run it, especially if you're tweaking the parameters. So for interpretation, you need to have some of Disney in particular. You need to have some extra external information that was not used in the embedding to color or label differently the results that you get, the compressed representations.
Perfect. Thank you.
Mm-hmm. And in terms of parameters, I don't have good recommendations because I don't have enough experience making teasing plots. I can ask around. I have workmates that have that information. I can send it around. Just remind me, because I'm probably gonna forget. Remind me on Slack later.
Perfect. Thank you.
Sure. Okay, we're running short on time actually. So I'll try to be very quick here. More or less talked about it. There was a discussion at the time. This is the archaeologist's role, trying to contextualize this paper as if it had been just discovered today. So there was a discussion going around at the time. A paper that came after this one, the year later, that referenced this, was this one visualizing the human connectome by Margoli and Gorgolewski and others. They discussed this paper in the context of human connectome data and how you present connectivity information. And they discussed the issue that was going on, that how do you say, data to ink ratio was small, and the types of information that was displayed was not conveying, just taking space and not really adding information to the readers. But that paper in particular is different than this one because they are looking at multimodal data. So they took the considerations from this paper, but only limited to that type of data, connectivity data. And then they were covering other types of data, including diffusion and other modalities. So their focus was rather different. Was bigger focus than this one. And just before this paper, there was a debate between Habeck, Muller, and Erhardt. Habeck and Muller were saying that figures were mostly ornamental in the neuroscience, especially regarding connectivity matrices and some of the brain images. And they were recommending just textual description because of that. And Erhardt came by and said, not so fast. The brain is spatial, so and words can only go so far. So if you use your figures wisely and display uncertainty, they become much more interesting and convey a lot more information that you couldn't describe with just words. An idea that I had, this is another role, this is the academic researchers, like what could you do moving forward from this paper, is I thought, a repeat of the same survey. Could call it visualization in neuroscience 10 years later. The hypothesis is that not much changed since 2012. And that's just a hypothesis, doesn't mean I believe it. But it would be interesting to see how things change since. Repeat the study, expand to other modalities, include, for context, the new tools and packages from across languages, Python, R, and etc. that are available today. And actually provide, expand on the types of tools that they provided in MATLAB to see if they can be reproduced outside of MATLAB in these other packages or languages. Yeah, and just for context, the private investigator role is like a background check on authors. The authors here were postdocs at the time in our lab, Eric Earhart and Elena Allen. And Elena was, I think, the head, she was the head author on this paper. She was very bright. That's basically what I have to say. She, I think, had a background in neuroscience. Eric had a background in statistics, and together they made a really good team. They I think were postdocs for a couple of years, and today Eric is a faculty, and Elena eventually went to industry. So that's the background on them, real quick. This is I leave as homework. I was hoping that someone would take the hacker role for this one, and maybe even explore translating these tools to other packages, or at least finding an equivalent way of implementing, reproducing those images in, say, Python, for example, or R, based on their MATLAB code. That would be a very interesting blog post, if anything, at least. So I'll leave that as kind of like homework if anyone is interested to, take a crack at it, and we could feature it next time we meet again. Like I said, we're already over time. I will stop here with the presentation and just open up for questions if there are any.
Thank you very much. Very interesting.
Yeah, thank you. All right, how many people do we have right now? I can't see.
6.
Yeah.
6 people.
So, yeah. Do you guys have any questions? Was anything not clear? Do you disagree with something? Would you like to see goes different direction? One thing that I was thinking was that maybe it would be interesting to get feedback on what date works better for people next time. If I were to send a poll on Slack discussing or asking about possible dates to hold the paper discussion, would you actually answer the poll? I noticed that not a lot of people answer the poll. So if I put a question there, would you guys be able to give me some feedback? Or you think that this time is fine?
No, I prefer to have a poll with the time.
Mm-hmm. Okay. Anyone else has a different? Okay. Okay, so usually do it either on Wednesday mornings or Monday afternoons here, Eastern time. So I'll give those options on a poll then.
Okay.
Yeah, and I'll do that before with define the paper itself, or what we're going to be discussing next time. One thing that I was considering, there are some interesting topics that are from book chapters. So I was thinking that maybe we could take like a section from a book for some of these discussions. I don't know if the format, using different roles would work well, because textbook information is kind of not old, but it's already well established, and it would be hard to put things in context, maybe. But what do you think? Is that something that would be interesting to look at specific techniques? There are some dense papers I'd like to cover in the future, and it might be interesting to have some of the background covered before that. Okay, I might make a poll out of that if you guys don't have feedback right now. Okay, so I'll do that. I'll ask those questions on Slack, and just to highlight it, it makes a lot of difference, and it helps a lot if you guys interact on Slack. So I'll put some questions in there, and if you yourselves, you can give me some feedback and get in touch with other people on Slack that you know to also help, to also reply. Will be awesome. And I highly encourage you in the future to take on these roles. They're not really hard. I actually went a little over the top today to actually go over the paper details. That's not actually necessary within any of these roles. So it's super useful to have this interaction, and I recommend you guys to at least find a buddy that can help you. And there are a lot of people in Slack that can would be happy to take you by the hand and help out. And you guys can work on this as buddies. That's fine as well. So with that comment, I'm gonna wrap up for today. Thank you so much, everyone, for stopping by. I really appreciate your time. I hope this was interesting. And if you have any questions about the paper or anything else, you can text me directly on Slack. And I think that's it for today. Thank you so much for stopping by. I'm going to stop the recording.